Hi, folks. So this week we're going to be doing the regression pre-lab, where we're going to be talking about correlation and linear regression. And as always, I sent you a Canvas announcement that has the pre-lab R Markdown document. You need to download that onto your computer, and then you need to upload it to RStudio Cloud. My recommendation is that you put that into the pre-labs folder so that all your file paths will work nicely. And if you need a reminder on how to do that, go back and look at the beginning of Lab 2, where I talk about the whole process. So as always, we're gonna start by loading our packages. I think you probably have these memorized by now. It's library mosaic and library GG formula. And then I can hit the play button to load those in. And then I need to read in some data for my labs. I'm always using the same example set, which is GSS. Then I'm going to do read.csv, parentheses, quotation marks, and then my recommendation is to use the tab, and then tab into the data folder and tab to that GSS clean.csv. And then if you press the play button, you should see the data in your environment, and you could scroll around in it just like we have every week. So we're going to do some exploratory data analysis. We're going to do data visualization for two quantitative variables, and then we're going to do some summary statistics. We're going to do correlation and regression. So the main data visualization we have for two quantitative variables is a scatter plot, and we're going to use our GF underscore plot functions. In this case, we're going to use GF underscore point. So point is the one that makes a scatter plot. It's not exactly the name of the plot that you want to make, but it's the name of the shape that you want the data to be. You want the data to be in points. So it's going to take a formula. So far, when we've been doing our GF underscore functions, we've been mostly doing graphics for one variable. So we've started with a tilde and then an x variable. Now we're going to have a y and an x variable. So we're going to use that y tilde x syntax. And typically we put the variable that we're interested in, like predicting, as our y variable. That's our response variable. And then the x is the one that we think might have an impact. That's our explanatory variable. So let's try this out. So I could do GF underscore point, parentheses, and then I'm going to put in some variables. So I'm going to try and predict the highest year of school completed, tilde, and I'm going to try and predict that using the highest year school completed spouse, comma, and then I always need to tell R where to look for those variables. So its data is equal to GSS. And then if I run that code, I should get a scatter plot like this one. So just like with last lab, we get a warning about some missing values being removed. In this case, 1,361 rows were removed of our 2,348. Again, we might not want to make linear regression based on this data because there's so much missing. Or we could say, you know what, we're just going to try and describe what data we do have. So here's our scatter plot. It looks like as the number of years of school your spouse has completed goes up, we'd expect the years of school that you had completed would go up as well. That kind of makes sense to me, right? People get married to other people who have similar levels of education, but probably not exactly the same. So maybe you went to a few years of college, so you have 15 years of school. That doesn't necessarily mean that you're gonna marry someone who had exactly 15 years of school. Maybe they only did 8 years of school, or maybe they did 20 years of school. So there's still some variability here. But overall, I would say this is a positive linear trend because it's going up. And I might say that this is a moderately strong trend. So sometimes we say, is it strong, moderate, or weak? And I would say this one is moderate. But that's a judgment call. I think it shows a positive association moderately strong. So now that we have done some data visualization, we think that there is some type of association, and maybe it's a linear association. We could use some summary statistics. So one thing that we could use is the core function, which stands for correlation, and that just takes the standard formula syntax. So it's core, parentheses, then whatever it is we're trying to predict, highest year of school completed, tilde, highest year school completed spouse, comma, data is equal to GSS. Hit enter. So it gives me an NA. So this is just like last time when we got an NA from our mean and median and standard deviation. The problem is here that the correlation function doesn't use the standard na.rm argument. Instead, we have to tell it what to use. And in this case, we'd like it to use complete observations. That's the ones where we have a value for the highest year of school a person completed and the highest year of school that their spouse completed. So we're going to add this use equal complete.obs, meaning complete observations, to the end of our function. I often work in my console, so I can use the up arrow on my keyboard to get to my old code. I need to go inside those parentheses. I'm going to put a comma, because it's another argument. And then I could write use equal, and then it needs to be in quotes, complete.obs. And now it gives me a number. So the correlation between these two variables is about 0.6. Correlation between the variables is approximately 0.6. And we could ask, is that a strong correlation or a weak correlation? You might have learned a rule of thumb from your professor. That's kind of moderate in my book, and that kind of makes sense based on what we saw from our scatter plot. Another type of statistic or statistical procedure that we might want to do is a linear model. So there is a function in R that does least squares regression. It finds linear models. It's called LM, which stands for linear model, and it also takes formula syntax. So we could just run this like in our console, LM parentheses, and then it's going to be the same stuff that we've put inside the correlation, inside the GF point. So I could just copy that out if I was feeling lazy, put it in there. I don't need that complete.obs thing, so I didn't paste it in, and hit enter. And now it gives me some information in my console. I'm just going to run it one more time because this is a little bit neater to see. So it tells us what our call was. It says that we put in a formula, which was the highest year of school completed by highest year of school completed spouse. So it's just kind of reminding us what happened. And then it gives us the coefficients. So it gives us the intercept value, which is 5.847, and then it gives us a slope value. It doesn't label it as slope, it labels it as the name of the variable that we're using to predict. So highest year completed spouse, and that's 0.594. Let's write out our linear regression equation. So the equation is y hat equal to 5.847 plus 0.594 times highest year school completed spouse. So this is one way to get the coefficients from your regression. There's usually a slightly better practice to do, which is to give your model a name, and then you can refer back to it later. So we've seen this assignment operator when we've been like loading in data before, where I made up a name for my data set. I called it GSS. Now I'm going to make up a name for my model. I call my models M1, M2, M3. You could think of better names to use. Like you could call this school model, something like that. I'm kind of stuck in my ways, so this is a do as I say, not as I do. So I say M1 gets, and so this is the assignment operator, it's going to put the result of all this code into that named object, and then I just put the same code again. So if I hit play on this, nothing prints out, but over here in my environment, now I have a new thing. I have my GSS data, and now I have something called M1, which says list of 13. If you click on it, you're going to get a bunch of stuff that doesn't make a ton of sense, so I don't really recommend doing that, but you can. And then the thing that's more useful is to run some R functions on that model object. So the most useful one is summary, and then parentheses. And then the argument that you give that function is the name of your model object. So M1. And if I hit enter, now I get a bunch more information. So I still get that call with my formula. It tells me some stuff about my residuals, and then it gives me this table of information. And this table still has my coefficient estimates. It's the same numbers we saw before, but they're down this column instead of being sort of written across in a row. So here's my intercept estimate, and here's my slope estimate. And then there's some other useful stuff that we'll come back to when we're doing inference for regression in a few labs. And then we could talk about interpreting coefficients. I have some generic sentences that I like. Your professor might have told you a different generic sentence, and it's fine to use that. When I'm grading your labs, I'll accept anything that's reasonable. But here's how I interpret the intercept. Maybe I'll go get my model equation so that I can look at that while I'm thinking about it. So I'm just going to copy this, and I'm going to bring it down here. Maybe make this bigger. So the intercept, that's this 5.847. When I'm interpreting that, I pretend like I've plugged in 0 for my explanatory variable, and then this would be my expected value for my response. So if the value of explanatory variable was 0, our model would predict that the response variable would be the intercept value. So let's try just plugging into that sentence. And for this class, it's totally fine to just plug into the sentence. In fact, we could just copy it and edit it. So if the value of the highest year school completed spouse was 0, so in other words, spouse completed no school, our model would predict the highest year of school completed for an individual to be, and then we plug in our intercept value, 5.847, and it's nice to put in units, years. So if your spouse had done 0 years of school, our model would predict that you had gone to about 6 years of school. And sometimes we talk about extrapolation. We don't want to predict outside the range of our data. It looks like we actually do have a couple people whose spouse completed no years of school, so maybe it's okay to actually interpret that intercept value. In some cases, plugging in 0 for the explanatory variable doesn't really make any sense. So the intercept is the less interesting one to interpret. The slope is the more interesting one to interpret. And here's my generic sentence. For a 1 unit increase in the explanatory variable, our model would predict a slope value unit increase/decrease in the response variable. So again, let's just copy this and then change it for our model. So for a 1, and then you have to think about what the units are. And in this case, they're years. For a 1 year increase in number of years of school completed by a spouse, our model would predict A, and then we plug in the slope value, 0.594. When we think about the units again, the units for this one are also years. It's not always the same for the explanatory and the response, but in this case it is. Year, and then we have to think, is it an increase or decrease? This is a positive slope, so it's going to be an increase in, and then the response variable is the number of years of school completed by an individual. So for a 1-year increase in the number of years of school completed by someone's spouse, our model would predict, or we would expect, or on average, you definitely need something like that in your sentence, our model would predict a 0.594 year increase in number of years of school completed by that individual. So that's one of the things that you might want to do with a linear regression model is interpret the coefficients. That could tell you something about a relationship between variables. Another thing that we might want to do is make a prediction. So there's more programmatic ways to do prediction in R, but for now, I think we should just use R like a big calculator. So again, I'm just gonna copy my model down here. Maybe I'll just stick it into my R chunk. So we're gonna try and see what the model would predict for a person whose spouse had completed 12 years of school. So they graduated from high school. So we've got our intercept plus our slope times, and then here's the highest year school completed spouse. We need to plug in 12 there. So if I click the play button, it says it would predict 12.975. So our model predicts that person would have completed 12.975, and we could round to 13 if we wanted to, years of school. Does that make sense? Yeah, it's about the same as the spouse, but not exact. And that kind of makes sense. And then another thing that we often want to do is think about residuals. So we want to know if our model is over-predicting or under-predicting for certain points. And we can compute a residual, which is the observed minus the expected value. Sometimes we call it yi minus yi hat. So we could look at row 21 in the data set. And to do that, I'm just going to click over to GSS. And I'm going to scroll down row 21. So this is someone with one child. They're 34 years old. They completed 15 years of school. So they went to 3 years of college. We don't know how much school their dad completed. Their mom went to 17 years of school, and their spouse went to 12 years of school. So if we wanted to find the residual for this person, we would plug in how many years of school their spouse had completed, 12, and we would get a predicted value, 12.975. And then we would do their real number of years of school completed, which was 15, the observed, minus the expected, or the predicted. And that's this 12.975. So I could put that into this code chunk so that it would show up when I knit my document. So the residual is 2.025, which is about 2. So they did about 2 more years of school than we would predict. We under-predicted their schooling. In this case, I don't know if it's bad or good to under-predict. For the lab, you might need to think about whether it would be better to under-predict or over-predict. So think about the sort of context of the data. So that is linear regression in R, and I think you've got all the skills you need in order to complete the real lab. You can start working on it, or I'll see you in synchronous class.